Hi students, today we're working on page 11, multiplying polynomials. So you're going to have to forgive me that there's already some writing on our sheet, but this is the third time I've tried to make this video and people keep coming in here, turning papers in or asking questions. So hopefully we can get through this video without any interruptions this time. So what they've done here is they're showing you a geometric model for multiplication. So if you're going to take 342 and multiply by 23, you can break it up, hundreds, tens, ones, kind of like the old school lattice multiplication. Then you multiply 20 times 2, 3 times 2, 20 times 40, 3 times 40, so on and so forth. Then you compare on the diagonal. 6,000 comes down. Then on the diagonal, combine these. 800 plus 900, 1,700. Then 40 plus 120 is 160. And then 6. So you take all of these numbers and combine them to be your answer. 6,000, 1,700, 160, and 6 all add up to 7,866. So this model just makes it a little bit easier if you're not good at multiplying large numbers, or if you don't know your multiplication facts. It helps you by breaking it into smaller, easier numbers to multiply. So we can use that same model for multiplying polynomials. So you just break up your trinomial into terms, and then I break up this binomial into terms, and then I just multiply. 2x times 2, 3 times 2, 2x times 4x, 3 times 4x, so on and so forth. Notice when I go on the diagonal, I actually have like terms. Okay, so I can combine them because they are in fact like terms. This is what I get when I combine. I write that out as one answer. Nothing combines any further, so that's my final answer. Now, it's a little bit trickier when you don't have like terms here, just because you have to notice the fact that you don't have like terms. The state goes through their model and shows you to add in this 0x. And then when you go on the diagonal, you actually get like terms. I think it's easier just to realize they're not like terms and write them out. But again, do whatever, float your boat. So I'm just going to rewrite this. Sorry, I know that there's already writing on it. But like I said, this is the third time I've attempted to do this video without interruption. So I'm just going to multiply x times negative 5. Negative 1 times negative 5. X times 6x squared. Negative 1 times 6x squared. X times x to the third. And negative 1 times x to the third. So now my diagonals, I have x to the fourth. These are like terms. Uh-oh, these are not like terms. So I'm just going to write them both down. Okay, and I'm going to write out the whole thing. I'm going to write it in decreasing exponential order. Oops, 5x to the third minus 6x squared minus 5x plus 5. This is my answer. They're kind of long, but that's it. Another way we can do this is by distribution. So this looks real complicated, and again, I'm going to make it simpler for you. What they're doing is they're taking every term of this trinomial and multiplying it by every term of this trinomial. So it's 3x times this. Sorry, 3x squared times this. 3x squared times this. 3x squared times this. Then x times this. Then x times this. Then x times this. Negative 1 times this. Negative 1. Okay, so on and so forth. So you can see they've written it out. The first term times the back trinomial. The middle term times the back trinomial. The last term times the back trinomial. Multiply it all out. Combine like terms. Okay, they do the same process here. I think it's easier just to draw on your loop-de-loops or just to distribute without writing it all out. If it's easier for you to write it all out, by all means, that's what you should do. I like to just do that kind of in my head. So s squared times s squared times negative 1, 4 times s, 4 times negative 1. Nothing to combine, so that one's done. Over here, order of operations. It's all multiplication, so left to right. Okay, so now it's this times this. Nothing to combine, so I'm done. Let's move down to number 4. Okay, so now this times this. Okay, now I look for like terms. S to the 4th, nothing goes with it. Negative S to the 3rd, and an S to the 3rd. Those are going to cancel. 4s squared, and an s squared, a negative s squared at that, gives me a positive 3s squared. Then a negative 4s and a 4s cancel out, and then I'm left with minus 4. And that's it. Now this one looks complicated, especially because they made it a square root. Just pretend it's a regular 5. Follow the same rules. So I start off just distributing the first one. So the square root of 5 times u, the square root of 5 times negative 1. Then I write out the rest. Whoops. That's u to the 5th, plus u to the 4th, plus u to the 3rd, plus u squared, plus u plus 1. So now this times this. The square root of 5u to the 6th, plus the square root of 5u to the 5th, plus the square root of 5u to the 4th, plus the square root of 5u to the 3rd, plus the square root of 5u squared, plus the square root of 5u. Okay, now I have to do this one, and you can see I've run out of room, so I am actually just going to move down on the next line. So negative square roots of 5 times u to the 5th is negative square root of 5u to the 5th, minus square root of 5u to the 4th, minus the square root of 5u to the 3rd. Hopefully you're noticing something's going to happen here. Minus the square root of 5u squared, minus the square root of 5u, minus the square root of 5. Combine like terms. Cancel. Apparently I have to buy new pencils. Nothing ever wants to work when I'm recording. Cancel. 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 I'm left with the square root of 5u to the 6th minus the square root of 5. I can't combine them because they're not like terms, so I'm finished. And that's it. Why don't you guys try numbers 5 and 7, and then go back to page 11 and try problem C on your own, where you actually make the geometric representation. So this was 11, and this page is 11A. So if you kept your packet separate, this one is in the other packet. Okay, so page 11, letter C with the geometric representation, and then page 11A, you're going to try 5 and 7. All right, we'll see you guys in class.